Class. The first problem I'm going to solve, okay, is one that's trivial, one where these angles are the same. And because the angles are the same, the tensions in each of these cables is going to be the same. And we can actually use that to solve the system of equations without resorting to something like matrices. Okay. So let's take a look at the picture here, right? We've got 5 kilograms, right? And so the force that's acting right here is downward, and what is that? It's 49.05, is that what it is? And that's 5 times 9.81, right? So 49.05 newtons straight down, right? And then we've got the tension on this guy, and we've got the tension on this guy. And since they're the same tension, I'm just going to call them T, like that, okay? Even though they're not drawn very well and they don't look like they're equal, let's pretend that they are, okay? Now, all you do for these things to solve these things is you draw the forces, right? Okay, so draw the forces, okay? Then draw the components. Draw the components of the force, right? And so this one's already just straight down. That's easy, right? This guy's got a force this way and a force this way, right? And then this is going to be T, what is this, cos 18, right? And this is going to be T sine 18. And really now I'm just using SOHCAHTOA. This is the opposite side. There's the adjacent side, right? Okay. And then this side here is going to be T cos 18. And this side here will be T sine 18. So the opposite side is T sine, hypotenuse times sine. The adjacent side is hypotenuse times cos. Are we good? I'm assuming you know that, but yeah? Okay. And then all you do, the first step is draw the forces, right? Second step is draw the components. And then the third step is set up an expressions in the x direction and the y direction that the sum, this little Greek symbol is the summation, right? So sum of the forces in the x direction is 0, sum of the forces in the y direction are 0. So the equilibrium means that the sum of the forces in the x direction add up to 0, in the y direction add up to 0. And if there was a z direction, those would add up to 0, right? And so let's just set up our expression here. In the x direction, what do we have? Then we have this guy in the x direction and this guy in the x direction. So we have one of the stupidest equations ever presented, is that T cos theta minus T cos 18 minus T cos 18 is 0. Can we solve it with that one? I think we could show that T equals T or something like that, can't we? You know? Isn't that sad? That's like one of those guys that races after the guy and tries to tackle him and then gets like nothing. Yeah? It's like, whew, right? Okay. In the y direction, though, things are a little more exciting because we've got this guy going on, we've got this guy going on, we've got this guy going on, right? It's like a battle between good and evil, right? You've got the upward forces. Will they hold out against the evil downward forces, right? Or if you're a fan of downward forces, it's the other way around, right? Yeah, right? Okay. So in the y direction, right, we've got, I'm going to make these guys positive, T sine 18, right, plus T sine 18, right, minus 49.05 is 0. So all the forces up minus all the forces down. Does that make sense? Equals 0. And if this, if these angles aren't the same at this point, we're settled. We have a matrix situation on our hand. Not like the movie, but more like the math kind of a thing. Kids are like, cool. All I have to do is pretend the math doesn't exist. And then this just becomes, 2t sine 18 equals 49.05, right? And then t is equal to 49.05 divided by 2 sine 18. Did I do that right? I think I did. Take your calculator and calculate what t is. Calculate that. I'm getting like 79 newtons. Do you guys get that? $79.4. I don't know how many sig figs we got. Only 2. Oh well. Are we good? Anybody else get 79? Please tell me if you didn't, We want to make YouTube more boring, but not more confusing. So that's sort of interesting, isn't it? This force, the tension in each one of those is more than the force we're supporting, yeah? 79 newtons in this one, 79 newtons in this one, and it's just holding up that. That's a bit surprising, is it? Or not? Yeah? Okay. So those bridges, you see those bridges. They've got one that goes over the railroad tracks at Union Station that look like this. They've got posts and posts, and they have a bridge deck, goes straight across, and then they have wires like this. You ever seen those? Very modern bridges, yes? Yeah, all those wires coming in at a grazing angle. The only part of the tension in those wires that's holding up the bridge is that vertical part, and the lower that angle is, like this, right? A lot of this one is holding up the bridge, right? But not so much of these is, right? Isn't that interesting? So it's the physics of it is interesting. The reason why they work is that, of course, steel is tremendously strong. It's very, very hard to stretch, right? And so these wires here that are going like that are just under incredible tension, but they can be. Steel is really, really strong in stretch like that. And then this deck here is made of concrete, and so the rest of that force is just acting to compress the concrete, which concrete is not very good in stretching. You can easily break it if you try to stretch concrete. But if you try to compress it, it's massively strong, right? So it's an interesting idea. Try it just for fun. Let's make this angle 5 degrees. Take your calculator. If you did it all in one step, go second entry, change the angle to 5 degrees. At 5 degrees gives me 281. Yeah? Try 1 degree. 1 degree. Oh, that's a lot of force. I get at 1 degree, it's, what are we approaching here? At 0, of course, the sign is 0, 0, and so the force is no, divided by 0 is like the idea of like infinity, yeah? Kind of a thing, right? Okay. Now, of course, it's not going to be infinity, right? At 0 degrees of angle, if it really were 0 somehow, right? Okay. So we neglect gravity. The weight of the thing doesn't deflect it. If it really were 0 somehow, and you exerted a force on the